It is my pleasure to introduce our next speaker, Shuddha Das. And the title of his talk is, you can easily see from the slide. Yes, please carry on, Shuddha.
Okay, thank you, Mrinda. Thank you, everyone, for coming and putting together this wonderful collection of talks. I want to bring in a new perspective to our discussion today. The usual approach to dynamical systems or even mathematics in general is analytic. This means that we start with some basic assumptions or fundamental assumptions about the dynamics. So this would mean assumptions on the properties of the dynamics transition law, assumptions on the space, assumptions on the phase space, and so on. And then we use these basic properties for some higher constructions, such as orbits, invariants, various kinds of invariants, mixing, and let's say asymptotic properties. And then there are higher and higher constructions. We can talk about ergodicity, we can talk about non-uniform hyperbolicity, Markov partitions, etc. So most of mathematical discourse has this is a hierarchy of ideas, and we prove theorems and we deductions and statements of theorems as well as deductions of proofs are based on the more fundamental ideas that are involved in the definitions. So, the perspective I want to offer today is a synthetic approach towards dynamical systems theory. A synthetic approach essentially means a category theoretic approach. In this view, one characterizes mathematical properties, theorems, and constructions not as consequences of the features or assumptions that are internal to objects, but only by their relations to other objects of a similar kind. So, this is the distinguishing feature of category theory. It's rather than a sub branch of mathematics, it's just a new formulation of results. The idea is that we take a bird's eye view of any uh, any subject matter. In this bird's eye view, we intentionally erase all the internal details and characteristics of an object, and all that matters are the relational properties of the objects. How are the objects related to other objects in that setting or in that collection? So there is a large effort underway to rediscover dynamical systems as well as probability theory and the theory of Markov processes, rediscovering this in the language of category theory. And it has still not gained sufficient momentum, in my opinion, and it would be great if more people joins this project. In particular, I'm interested in knowing how much of this categorical perspective would seem relevant uh, to some of our speakers today who work with fractal sets and paths in iterated function spaces, because it's my belief that category theory bypasses a lot of the complications of non-smooth geometry. And There's a lot of ground to cover today. Uh, let's see how much I can cover. But in the very least, what I want to convey to you is the idea of a path space. So a path space is the collection of all sample paths of the given process. So it's not just a deterministic dynamical system. Given any stochastic process, we can talk about their path space. In fact, one of the earliest perspectives towards stochastic processes by Kolmogorov, by Doob, was that we should in fact characterize any stochastic process as a shift invariant measure on the space of sample paths. So what uh, in the very least, what I wish to convey to you, to my audience today, is this idea of a path space and how it can be constructed, not by the usual pointwise or set theory definitions, but by something called a universal property. So it'll be the construction will be very diagrammatic. The language of category theory is diagrammatic or pictorial, and it's universal in the sense that I'll claim it to be a picture which is unique and which covers every other similar picture. We'll understand the details when we get there. So let me begin by drawing a picture of three semi-groups actually. So this is a simple illustration of the additive semi-groups of non-negative integers, integers, and real numbers. And of course, there are many more groups that exist. The reason I'm depicting these groups is because they often play the role of time. These are the usual choices of time structure in dynamical systems theory. So observe that I have uh, depicted the elements of the group, each element of the group as arrows starting and ending at the same object. So the reason I've chosen this particular representation is because it helps me uh, understand what a dynamical system is from a categorical perspective. A dynamical system consists of a phase space, let's call it omega, and a collection of endomorphisms. So here I have depicted the action of, uh, what I'm depicting here is the action of a semigroup. The semigroup I've chosen for illustration here is the semigroup of non-negative integers. So observe that the semigroup property of integers with respect to addition is transmitted into the composition laws for dynamical systems. So this is a basic idea that we will try to take this diagrammatic view of any construction and any notion. And one can have a similar, very intuitive diagram for semi-conjugacies, but here is a here is an elaboration of what I have drawn in this slide. See, here I have a phase space. Let's call this X. Now there can be many, in fact, infinitely many self maps or endomorphisms of this object X. So in our narrative or in our analysis, we are not going to uh, discuss any finer properties of these maps other than the fact that these are self-pointing arrows or endomorphisms. Now, not every such endomorphism will be covered by a group action. The semigroup action phi can be interpreted as an engraving of the existing time semigroup into the larger semigroup of endomorphisms of the object. So up till this, it might be quite familiar to practitioners of dynamical systems theory who work with group actions. Here is a diagrammatic representation of what we mean by a semi-conjugacy. Here, this picture depicts a semi-conjugacy H between two dynamical systems, which I have denoted by phi and phi prime. So it means that essentially we know what it means, that these two dynamical systems evolve in tandem and they're forever bound by these commutative squares. So we'll see that all of these are expressed very succinctly in the language of category theory. Dynamical systems themselves become object of a certain category, and semi-conjugacies have a very nice interpretation as natural transforms. So let me quickly review what a category is. A category is basically, the definition of a category is very minimalistic. It's essentially a collection of objects and a collection of arrows or morphisms connecting the objects. So of course we want more. We would want a certain compositionality of these arrows. Arrows should be composable end to end. And this composition should satisfy certain basic laws, such as composition remains invariant under composition with the identity morphism, composition should be associative, and so on. So this is very reminiscent of a network or a graph. In fact, if you consider any network, say on n vertices, the network itself is not a category, but given any two nodes in the network, the collection of paths from node A to node B could be interpreted as a morphism. So paths have a compositionality and the path structure of a network is a category. So for our purposes, one of the most important examples are semigroups themselves. Any semigroup, so which means also any group is also a category. We can represent any semigroup as a one object category. And each element of the semigroup corresponds uniquely to some arrow of that category, which means the compositionality of the semigroup structure is translated into compositionality of categorical composition. And these are also some of the most important examples of categories. So set is the collection of all sets. So I should be careful when I say set of all sets. So rather I should say the collection of all sets up to a certain cardinality. So that's a well-defined collection. And if we allow all possible maps between such sets, we get a category. Of course, maps can be composed with each other and it is associative. Similarly, if I impose some more structure, I get some more structure on these sets, and also, which means also on these maps, I get more structure and different categories. So mesh represents the category of measurable spaces. The objects are measurable spaces. The morphisms or arrows are measurable maps. Topo is a collection of topological spaces and continuous maps. Manifold R is a collection of R-dimensional manifolds and CR smooth maps. Vec is the collection of vector spaces and linear maps, and so on. So realize that each of these categories that I listed at the bottom of the screen can serve as a context for a dynamical system. We can talk about operator families of dynamical systems. Then our category is the category of Banach spaces. We can talk about measurable dynamical systems. When we talk about stochastic process, that corresponds to a different category, also a dynamical system. And we can just talk about, as is often the case in computer science, the dynamical systems discussed in computer science are usually just set theoretic. And one more basic notion to learn is the idea of a functor. A functor, very simply put, is a function that preserves structure. So here, of course, structure means categorical structure, which means a functor between two categories is a function or a mapping that maps objects to objects and which map arrows between two objects to another arrow between the corresponding pair of objects. And of course, it should preserve identity and compositionality. So let's observe that the first thing to observe, now that we have an idea of what a category is and what a functor is that a dynamical system, any dynamical system, can simply be interpreted as a functor. This is one of the most effective and simple descriptions of a dynamical system that I have seen. And of course, there can be different choices of the time structure. We can have different choices of the semigroup structure, as you see on the left of the screen. And we can have different choices of the context category, which I've denoted as C for context. So depending on the context, depending on the choice of time structure, we can call it a continuous or discrete, invertible or non-invertible, depending on whether it's a semigroup or group. Similarly, depending on whether it's topo, measurable, Banach, etc., it will be a topological dynamical system, measurable dynamical system, etc. So this is our first step into the categorical description. analysis less difficult or less hard. What it does is its category theory is an excellent organizational scheme. So think of all the properties, lemmas, and theory that go into establishing a theorem in dynamical systems. What what happens in a category theoretic description is most of these assumptions are present, but they recede into the background. These assumptions are incorporated in the choice of the categorical context. And assumptions assumptions about the map, the nature of the map, that is directly encoded into whatever arrows or morphisms are allowed by the category, and assumptions about the face space itself. So let me jump back a few slides. So here X. So in a categorical description, I have no more information. I have no information about the content of X, the internal features of X. So, but this is the magic of category theory. All this information is encoded via the relations of X with other objects. So it's encoded inside the um, morphisms or arrows that are outgoing from X and are incoming to X. In fact, this is one of the key principles of topology. Any topological space is completely characterized by how other topological spaces map into that space. This is the idea of the simplicial decomposition and simplicial approximation. A very similar idea also holds in linguistics. A word does not, the words that we speak do not contain meaning by themselves. The meaning of every word is actually upheld in the relations a word holds with respect to other words. So that's the viewpoint of category theory. It doesn't make math harder or easier, but it's a nice organizational scheme. And what happens is that a lot of the assumptions are encoded in the category or in the external description of the object. The proofs or deductions themselves are no longer analytic, they are pictorial. So we now look for diagrams, something called diagrams, which are patterns, and we try to establish universality of diagrams, or we try to find diagrams embedded within other diagrams. We'll see some examples. So, as I mentioned before, any dynamical system is a functor from a time category T into a context category C. So it turns out the collection of all such functors itself is a category. So this is like a second layer of category. This is a second layer, or, or this is a hierarchy of categories, a second layer of category, which I'm denoting by DS for dynamical systems, built over the context category C. And so, of course, for a collection to be a category, we need objects as well as arrows, morphisms. The objects here are every functor becomes an object. The semi-conjugacies, they become arrows in this category. They have in categorical terms, these are called natural transformations. So, so before we get down into description of some familiar dynamical properties, uh, let me explain that just like arrows can be composed with each other, in in the usual context that we work with, objects can be composed or joined with each other as well. So we call such categories a monoidal category. So here are some examples. Again, most of the examples that we have already seen has made an appearance. Set, and also let's take note of the fact that there can be multiple ways by which objects can be joined with each other. So of course, in most contexts, Cartesian products is an option, but often there are other options as well. So we are looking at specifically at dynamical systems which are functors from a time category into a monoidal category. Secondly, I'll make a point here. As I was saying, there's no in a category, we intentionally erase all internal details of the object. A topological space is only represented as a dot when I'm putting it down on paper, but all topological properties are still preserved they are preserved collectively, either incoming or outgoing. So this is known as the famous Yoneda embedding theorem, that if it either given any object X, it is completely characterized by the incoming arrows or equivalently by the outgoing arrows. So this is the collection of incoming or outgoing arrows. These are known as the collection of homomorphisms, or the home set, in short, HOM. So here is one last categorical terminology to be cognizant about. Miralda, how much time do I have left?
Yes, you have time.
I have time. Okay.
Yes, yeah, 9 minutes.
9 minutes. Okay, thank you. Yeah, I'm close to introducing my main topic.
Yeah,
So,
take 5 minutes, then people may ask questions.
got it. Yeah. So, let's see this. So, suppose I have a category. It could be our context category. It could be my dynamical systems category. And suppose it's a monoidal category. Here on the left, I've taken a monoidal product, some kind of product, could be a tensor product or a Cartesian product of two objects. And I can look at the arrows from y times x to z. Certain categories have this property that I can form a special object denoted here in square brackets called the internal homomorphism object. One of the breakthrough discoveries of or concepts of category theory, such that for every object X we have this natural bijection of home sets, meaning there's a one-to-one correspondence between all arrows from an object X into the internal home object YZ and arrows from YX to Z. So let's try to unravel this from a set theoretic perspective. Given any two sets, Y and Z, the collection of functions from Y to Z is itself a set. So that is what is being generalized here. We can consider the collection of maps from Y to Z either as a home set. It is also again an object of the set. So any category which enables such a representation, in which the bundle of arrows between Y to Z itself can be encoded as an object, we call that a closed monoidal category. So this idea enables some very fundamental. So we talk about these purely categoric ideas, and we see many familiar ideas from dynamical systems taking shape. For example, if we consider the internal home object omega comma omega, basically we are bundling all the endomorphisms of omega, and we are encoding it back into an object of C. We call this the endomorphism object of omega. This is no longer a collection. The home sets that I've written here, that's a true collection or a true set. It has got nothing to do with the context category. However, these objects are again, endomorphism objects or internal home objects are actual objects of the category C. Similarly, another important consequence is that the time subcategory can be encoded as a certain object which I've denoted as boldface T. So this is the representation of time as an object in my context category. So think of think of any group. If the group has a topological structure, I can also interpret the group itself as a topological space. Only then can we talk about continuous dependence of the endomorphisms on the group. The same holds for differentiable, a group action that is differentiable with respect to the group elements. And finally, we come to the idea of a path space. The path space is the internal home object. Path space of any object X corresponds to the internal home object of the time object and omega. So I've been talking a lot about the internal home object. When is this possible? I'll wrap up by saying that the idea of studying dynamical systems as a functor from time semigroup into a closed monoidal category has been a relatively recent advance, a recent idea, and there are some obstacles. Not every category allows a closed monoidal structure. So here are some examples. So in particular, if we want to study topological dynamical systems, we have to make some adjustments to the category. It cannot be the entirety of all topological spaces, but something called compactly generated weakly, there's a type weakly Hausdorff spaces. Similarly, instead of all measurable spaces, we have to talk about quasi-Borel spaces. And so I will end here. I will point, I will point the readers to our main result and also provide you with a reference. This is something that has been under revision for more than a year. But the basic idea is that I'll end with this. Any path space has a natural time shift along it. It's just shifting the action of the semigroup itself leads to a shift flow. Also, any time space leads to a natural transfer operator, which is familiar to anyone working with operator theoretic aspects of dynamical systems. It's manifested often as the Perron-Frobenius operator. What we can show, and this argument is purely diagrammatical, purely pictorial reasoning, and context free of context other than the assumptions on closed monadal structure, it is that the embedding any dynamical system can be embedded, any dynamical system on the phase space omega can be embedded into the path space of omega. And this is the image, which is the intersection, the unique intersection of the shift dynamics and the transfer operator. So this has further consequences. I would be glad if any of you take a look at our work and provide your reference. But more than that, I welcome all of you to join this project, which is still very scattered on rediscovering dynamical systems using the language of category theory. And I'll end here. Thank you very much.
Thank you. Is there any question to the speaker? If not, let us thank the speaker again.
Thank you everyone for your patience.